So before we can talk about the Doppler effect, we have to understand pitch. And to understand pitch, we have to remind ourselves some things about sound. So some things we've talked about sound. Sound is an energy that's being carried by a wave. Specifically, it is a longitudinal wave. All right. So again, that's the one that has compressions and rarefactions. So again, that's the one that looks like a slinky. All right. So the areas where the slinky is close together is what is called a compression. The areas where the slinkies are spread apart, that's called the rarefaction. And so again, we can also determine wavelength on a longitudinal wave as well. But one of the main issues here is this, though. Sounds are produced by vibrations. So things have to move or vibrate in a quick and short pattern to produce sound waves. So again, you can hear my voice because my voice box, which contains my vocal cords, is producing sound. And those vocal cords are producing sounds by vibrating. All right. And the reason why the cords vibrate is because the air from my lungs are passing through them. And as they pass through them, they vibrate the cords, and therefore the vibrations produce the sound, which is why sometimes when you're congested or if you have a cold, you sound differently, and that's because a lot of times your vocal cords are covered in mucus, and when it's covered in mucus, or that slime, I guess we could say, it causes the vibrations to be different. So it affects how it vibrates, which therefore affects how you sound. So very much your vocal cords work in the same way as a guitar string does. A guitar string just sitting there doesn't make a sound. But if you pluck the guitar string and it causes it to vibrate, then you hear a sound from the guitar. And so it's the same idea there for your vocal cords. And so, but again, the vibrations, sounds are made by vibrations. Vibrations are made by your vocal cords, and then they travel through the air in longitudinal waves. Then the sound waves get to your ear, causing your eardrum to vibrate. That produces the sound in your ear canal. Your brain then takes that sound and then kind of, like, I guess you would say, transmissions it to your brain so that it makes sense to what you're hearing. That's how you're able to distinguish one sound from the other sound. So that's what we're dealing with here. So sounds are vibrations. They are carrying energy, and they are being carried by waves. And so they do go from one point to another point, which in this case specifically is from my voice to your ears. All right. Now, sounds can be different. All right. Obviously, there are different sounds that can get your attention. So again, like for example, the sound of my voice sounds different from the sound of a key getting in the door lock, right? So because again, when you hear the key in the door lock, that's a different sound than my voice, and so you start looking at the door to see who's coming into the room. So that's one thing. Another sound that you may have heard this morning, it might have been like tires, screeching or squealing on the pavement, right? So again, usually when you hear somebody hit the brakes and you hear the tire squeal, right, that usually gets your attention. So sounds are different quality. All right, which makes you distinguish one from the other. And so one of those distinguishing characteristics of sound is going to be the sound of the issue of pitch. All right, and so, but what we want to know right here is this. Oops, sorry, let me go back. The speed, we talked about the speed of sound the other day. All right, as a matter of fact, I was scrolling to a Twitter thing. All right, and on one of them, because I look at one that's called like physics or something like that, and it has a picture of, or has a video of a plane breaking the sound barrier, right? And so if you ever seen a picture or seen a video of a plane breaking the sound barrier, you'll kind of see this like conish cloud behind the plane, because that means the plane is traveling faster than the sound it's producing. So it's going so fast that it's going to get there before the sound gets there, which is why most of the time if you hear a plane that is breaking the sound barrier, you see the plane, and then later, in a few seconds, then you hear the sound of the plane go by. So that's kind of an unusual feat for it, something to accomplish there. As a matter of fact, it wasn't accomplished for a while. But the speed of sound, all right, is affected by what it's traveling through, because sound waves, they need a medium. So again, we said that a medium, hold on, don't say it, Donovan, because I know you want to. Mahomes, what was a medium again?
The material that wave.
That's right, the material that the wave is going to travel through. So again, just as a reminder, Wakanda, my voice is traveling through what is the medium that my voice is getting to get to your ears?
The sound.
Yeah, but what is the sound traveling through? What is the medium? What is the material my voice is traveling through to get to your ears?
Air.
Good job, Coburn. All right, so it's traveling through the air. All right, so air is a medium. All right, and air is in which form here? Solid, liquid, or a gas?
Yes.
It's a gas. All right, And so, but we talked about this the other day, right? So if sound is traveling through a solid, or if sound is traveling through a liquid, or sound is traveling through a gas, which one can sound travel through fastest? No. Solid. And the reason why is because when you talk about the particles, remember we talked about the kinetic theory of matter, all right, when we were talking about heat, all right, we said that all things are made of tiny moving particles, right? So again, solids, those particles are close together. They're not moving around much, all right? So you think about it like in the case of a kid, right? Who's easier to catch? A kid playing PS4 or a kid that's running around on the playground? That's right. So therefore, the molecules in a solid are like a kid playing the PS4. They're not really moving around that much, so it's easier to catch them. So when the energy has to get passed from particle to particle, well then the closer those particles are, the easier it is for the transfer to be. The gases, they're all over the place. So therefore, to try to get one particle to the next particle, that means you got to catch one kid, then that kid's got to catch another kid. It's like playing tag, right? When you're trying to avoid each other, then it's kind of hard to make that. It takes a little bit longer for the message to get to the other side. But the second thing here is temperature. Cool or hot? Which one of those, don't say anything, Donovan, yet. Which one of those do you think causes sound to travel faster through? All right, so for that one there, let me go to Alondra. Which one? I can already tell by your look you're guessing. Hot. All right. Eric, what do you think? Same thing? You think cool? All right. Jenny, you break the tie. Hot. All right. The answer would be cool, because remember, when you're cool, you have less energy, which means you're not moving around as much. So it means particles are not moving around. They're closer together. And so therefore, it's easier to pass the information from one particle to the next particle. All right. So again, this here is like trying to get a message to the other side of the school, but everybody in between is playing tag. Here, they're not playing tag. Here, they are playing tag. So again, the energy is able to travel faster through colder objects and through solid objects. All right, are we good with that? If you need more time, say time. All right. Now, the next slide is going to deal with pitch, P-I-T-C-H. All right. Now, pitch, for those of you who ever do anybody know what pitch is? Go ahead.
It's like I'm not explaining, but it's like how high or low.
Okay, so how high or low, right? Where do you normally see, where people normally dealing with the word pitch?
Like when they sing.
When they sing, right? So therefore, that's when you talk about pitch, like how high or low that you sing, right? Well, that's kind of the same idea. So pitch is basically how the highness or lowness of sound, but that's directly connected to frequency. All right, so let's remind ourselves of a couple things about frequency. All right, so Jordan, tell me, what is the unit of frequency, first of all? Coburn? Hertz, all right, it dawned on him at the last second. Oh, hertz, all right. So hertz is a unit of frequency, and how do we determine frequency? So if I gave you a wave, how are we determining frequency? Hold on, Jayla. What about it then? If you're going to give me that answer, I'm going to have to make you elaborate. What about wavelength? Don't know? Jayla? Sorry, not Jayla. Donovan? I didn't.
Wait, what was the question again?
The one you were about to answer before, when I said hold on?
Yeah, you supposed to count on the crest and the trough.
Okay, so counting crests and troughs. All right, so now tell me something about frequency then, using crest and trough.
It's like, okay, so if there's like 4 crests and 3 troughs, you're supposed to get like a number in between them both. But if they're the same number, then that's your frequency.
Okay, so tell me this. I have a wave, it's got 5 crests. I have another wave, it's got 15 crests. What do you know about those 2 waves? How about this? 5 crests, 15 crests. Which one's got a higher frequency?
15.
Okay, that's the connection that we're trying to make sure we understand, right? Which means if you got 15 crests, Jayla, right? Tell me something about the wavelength of the wave that has 15 crests compared to the one that's got 5 crests.
It's probably small.
All right, it's probably smaller wavelength. Okay, so therefore that's the connection Jayla was trying to get to, which is wavelength and frequency are related, but they're oppositely related. So if you have a bigger wavelength, you have less of a frequency. If you have a shorter wavelength, you have a greater frequency. All right, well, that's what we're getting to here now. Pitch is dealing with frequency. So when we're going to move on because we already answered those before. All right, pitch is the highness or lowness of sound, just like Mahomes said, right? But now what we need to understand is, well, the highness or that lowness is attributed to frequency, okay? And what we need to really make sure we understand that, because again, we have a lot of connections that we got to deal with. Like I just gave you one that Jayla was trying to tell us, which is the wavelength connection to frequency. That connection is greater wavelength, lower frequency, all right? Or if we're going to flip that, smaller wavelength, greater frequency. That was that connection. Well, here we have another connection. The connection here is between pitch and frequency. So what we need to know is what is the connection between frequency and pitch? All right. So like now I would know this. I know something with a high frequency has a small wavelength, but what does something with a high frequency have in relation to the sound of its pitch? Okay. So a sound wave with a high frequency, what kind of pitch would that have? A sound wave with a low frequency, what kind of pitch would that have? As a matter of fact, let me go ahead and throw that line up there because we got two blanks we want to try to fill in here. So my question is this. Hopefully nobody's feelings are about to get hurt, but let's find out. Alondra, say the United States of America. Oh, wait. Before you say it, everybody listen to her voice, because you're going to be comparing her voice to another voice. Got it? So, everybody listen to her voice as she says it. All right? 1, 2, 3. The United States of America. Okay? 1, 2, 3. All right? Everybody heard that voice? Okay? You heard her pitch, because we know it's highness or lowness, right? Okay. So now, I'm going to say it. The United States of America. Right? So now if we go and say highness and lowness, out of the two of us, who had the higher pitch? Y'all thinking too hard. That makes my feelings hurt now. She had a higher pitch, right? Who had the lower pitch? Me, right? So usually like in the case of like when like people who have more bass in their voice, that's going to be usually a lower pitch. Okay? Bass is a lower, all right, pitch in the musical scale, right? Then you have the higher pitches, which are usually going to be your altos. All right, your sopranos, things like that. Those are going to be your higher pitch voices. Usually in choirs, usually women are in the higher pitch zone and men are in the lower pitch zone. Because usually, all right, more times than not, all right, that men have lower pitch voices than women do. All right, that's not a guarantee because there are some women who have deeper pitched voices. All right, and then there are some, never mind, we won't go in that category. So, what we need to do, though, is we need to connect the dots here, though. So if it's easy for us to now understand that Alondra has a lower pitch, the question now is, so does she have a lower frequency or does she have a higher frequency? So what do you think, Alondra? It's your voice. What do you think? Do you think you got a lower frequency voice or a higher frequency voice? Lower? Okay. Well, let me add this statement now. So now I'm going to answer this question, but I'm not going to answer these questions. I'm going to see if you can put 1 + 1 and get 2. All right. Sorry, I'm at North Pitt. So here's the statement I want you to know. Okay. Frequency and pitch are directly related. Okay. Frequency and pitch are directly related. So, who haven't I called on yet? So Kevin, okay? Frequency and pitch are directly related. You do agree that I have a lower pitch voice than she does. All right? So then do you say that my voice is lower frequency or higher frequency? Now that you know frequency is directly related to pitch.
Higher.
All right? If it's directly related, then that means low pitch, low frequency. That's what directly means. It means if it's good for one, then it's good for the other. All right? So directly related means low pitch, low frequency. So higher the frequency, what should go in this blank? Higher the pitch. Okay? Lower the frequency, then lower the pitch. Got it? And if you don't remember what pitch sounds is, again, you can listen to Alondra. You can put Alondra next to the higher pitch. You can put my name next to the lower pitch, right? Matter of fact, be careful. Sometimes they might hear another name of the launderer that sounds like pitch, but maybe not. All right. Are we good with that right there? Okay. So now, what frequency range can the healthy human ear hear? Okay. Now, this is a range, which means some of you may not have the full ends of this range. You should, because younger ears should be able to have a wider range than older ears, but younger ears usually do things that could damage the ears, which is listening to loud music, all right? But at the same time, there are other things that can cause you to lose some of the abilities of your ears to hear frequencies, and that's if you work at jobs with loud motors or loud engines. Like if you work at an airport, right? If you've ever been in a plane, you ever see the people outside, they always have those big ear covers on, right? That's to protect their ears, because those high-pitched frequencies, after a while, they can cause damage to the nerves in the ear, which send a signal to your brain, and therefore then you don't hear certain frequencies. But the normal frequency range for a human, all right, that's not a FYI. Don't think that's a negative. No, that's not it. That's a negative. So negative 20 hertz to 20,000 hertz. I wanted to make sure that was a negative or a dash, but now that I think about it, it's a negative. So they can hear negative 20 hertz to 20,000 hertz. That's the typical range. Now, if you've never been around older people, and let me qualify older people, all right? Older people mean for me is like 60 or higher. All right, that's older people, because again, that's usually where those individuals like 60 or higher. Normally I used to say grandparents, but now there's grandparents that are like 36 years old. But what was I saying? They have a problem hearing high frequencies. So a lot of times, if you have like females, when they speak to them, it's hard for them to hear them. Like they'll talk and they're like, huh, right? Because they can't hear the high frequencies. Now, dogs can hear higher than that frequency. So have you ever heard of a dog whistle? Yeah. Right? And so again, you know, if you ever blow into a dog whistle, do you hear it make a sound? No, but the dogs do, because the whistle there is such a high frequency, such a high pitch, that you can't even hear it. All right? Sometimes you guys scream, and your voice gets such a high pitch in your scream that your scream kind of just fades because you can't even make the sound anymore because it's so high. And so that's kind of the same thing. So the healthy human ear can hear a range of negative 20 hertz to 20,000 hertz. That's a really high frequency. Now, let me go to the next slide. Are we good, by the way? Okay. I'm going to let you write this down. There's a whole range, all right? I'm only giving you two, ultra and infra. Like, there's a whole range of frequencies that we could describe, but I'm only going to give you two, the ultrasonic and the infrasonic. What was the top end of the frequency that our ears are typically able to hear? 20,000. Okay? So here's what I'm going to do. I'm going to hit a note here that's going to let you know so you can kind of see how impressive that range is. All right? So for example, right here, I'm going to hit this tuning fork, which is going to produce a sound that has a certain frequency. The frequency of this tuning fork is 256 hertz. So this is what 256 hertz would sound like, okay? Okay? Matter of fact, when you hit that, when the tuning fork hits the table, there you go, all right, you can feel the vibrations in your hand. If you take it to your ear, you'll actually hear the vibrations, and then if you get close enough, it'll actually move the hairs on your ear, and then it'll tickle. Like that usually what the tickling sensation is when the hairs on your skin or the hairs wherever, all right, are moved. That sounded odd. I meant to say like in your ear or your arms or whatever. So, but anyways, they get moved, and that's what kind of creates that tickling sensation. So that's the same thing here. So that was 256 hertz. Here is 288, right? So should this one sound higher or lower in pitch? Higher. So here we go. Here's 288. Okay, so there's 288. All right, so some of you are going, that's kind of high, like that's kind of high pitch, right? And imagine though, your ear can hear, let's see, that was 288, right? So let's go, it can hear 1,000 times more than that. 1,000 times higher than that it can hear. All right, here's the highest one I have, which is 493 frequency. Okay, so here's this is about the 400 hertz range. Okay, so I'm just kind of letting you know that's what the different frequencies sound like. None of those were above ultrasonic, which then again, ultrasonic wouldn't bother you because you can't hear it anyway. All right, but ultrasonic does serve purpose to us. Sonar is in ultrasonic. All right, so like fishing boats. If you ever have some people who go fishing, they have sonars because then it can detect the depth of the water underneath them. So they can also, and they also can detect where the fish are. So if they're fishing, they can kind of hunt for fish. It sends out signals, and then when the signals hit something, it kind of, the way it works is signals get sent out and signals get sent back. Well, the signals that don't get sent back, it lets them know that there's something there, and so it can kind of map out how things are underneath the water. Bats use the same thing when they fly, because bats, again, they fly at nighttime. They do their thing at night. They are nocturnal. So bats, they don't see. They move around through sense. So they send out these signals, and basically when the sound comes back, it lets them know that there's something there, so they need to avoid it. A matter of fact, a lot of blind people will use that same thing. You ever see a blind person who has the stick when they're walking around and they're going like this? Right? Well, the whole point of them doing that clicking sound with that is they click the sound so that they can hear if the click echoes off of something. And if it echoes, like if they're going over here and they hear something echo off that desk, they go, there's something there, so I better kind of come over here now and walk this way. That's how they kind of navigate, because they can't see. They're blind. So they use their hearing for that. And they use their hearing by using sounds, in a sense, very similar to how bats use their sound. But bats, their sound is so high-pitched, we can't hear it. You can obviously hear the clicks. Infrasonic are below frequency, so like thunder. All right, these are the ones that you don't really hear, but you kind of feel. All right, so as a matter of fact, sometimes I can't tell the difference between thunder and my stomach growling. All right, so sometimes I get nervous thinking that it's either a storm getting ready to happen, it's just me being hungry. But sometimes you can get that same, because it's caused the same vibration, right? Whenever thunder happens, the house shakes, you shake, right? So sometimes I'm thinking it's just me, but it's thunder. All right, are we good? I know there was a lot of writing on that one there, but hopefully we're kind of good with that. The next slide won't make sense to you, but I taught, oh crap, what was his name? Corell. All right, so I had a joke with Corell. And so that's why the next slide is what the next slide is. But let me know. Where are you at there, Jess?
The last two.
Last two? All right. Thunder. Anybody hear any thunder last night? Mm-hmm. No? You shouldn't have, because it didn't rain, so I didn't. But then again, I was trying to see if somebody would just say yes. But I never know. Subsonic. Yeah. Remember, all these are the ones that you don't hear. All right. Now, frequency is different than intensity. Intensity is something that measures how loud the sound is. So making sure that we understand the difference here. Frequency is the highness or lowness of the pitch, but that is not volume. Volume is intensity. Okay, so when we talk about volume, we're talking about how loud the sound is. Not the highness, not the pitch, but how loud. And that's measured in decibels. Okay, that's measured in decibels. All right, here's the Corell Robertson slide, because this is him. All right, so I put that up there because I used to always say, man, why are you trying to look like Sid the Science Kid? Because of his hairdo. And then he'd always make jokes. All right. All right. You know what? I'm not going to write that. Don't write that. Don't worry about it. If you're watching this video, don't write it. Okay, let's get to, come on. Thank you. Let's get to the main topic now. Here's this. So now we can talk about the Doppler effect, because now we understand sound is produced by sound waves are produced by vibrations. Those vibrations have frequencies. Those frequencies can be high or low. The high frequencies are high pitch, and the low frequencies are low pitch. Now, the Doppler effect is a change in pitch, meaning it's a sound that will change in pitch because something is moving. Whether it be you're moving or whether it be the object producing the sound is moving. So like a Doppler effect is something you will notice for one of two reasons. Either the object is getting closer or away from you, or you are getting closer or away from the object making the sound. So either the sound producer causes the change or the sound receiver causes the change. But that's what we're dealing with there in the case of the Doppler effect. All right, in the case here that I have there, Mr. Coburn, is this. What is that thing right there at the bottom? An ambulance, right? And what do you think is producing the sound in the ambulance? The siren. What else produces sirens? Come on, you should know something else that can produce a siren. Okay, if like a fire truck. All right, hold on. Kevin, what else can produce a siren?
Police car.
There you go. All right, there you go. See, I was like, how did you not say police first? That's the first thing I heard you. I'm just trying to say, like, I'm figuring Coburn would. Coburn had been pulled at some point in his life. Okay, so. All right, so sirens. Now, notice, well, Coburn drives. So, you ever had that moment where you hear the police siren behind you, and then you get nervous? You're like, oh, God, he's going to pull me. And then it drives past you? Have you ever paid attention to the sound of the siren as it passes you and how it sort of changes? Well, that change of sound, that change in pitch, that's what the Doppler effect is. Okay? Remember yesterday when we had the guy making waves in the water, right? And it had those circle rings kind of coming out? This is the same idea. It's the same kind of way we're dealing with here. All right? But now here's the issue. And here's the most important part that you need to remember now, is this. This is the key line. Because we now know the Doppler effect is a change in pitch, but then the question is, how does the pitch change? Well, the pitch changes, all right, in two different ways. If you get closer to the object, the pitch is going to increase, all right? So as you get closer to the object, it will sound more like Alondra. But as the object gets away from you, it's then going to start sounding less like Alondra and more like me. So the pitch is going to go from, as it gets closer, pitch gets high, 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 high. But then once it starts passing you, it goes from high to low. All right, and so that's kind of what you hear. We're going to watch a little video here in a second that's going to demonstrate that sound that you usually hear in traffic, especially when somebody blows their horn or if somebody has a siren that's going behind them and that gets past them, and they're relieved because they didn't get pulled over by the cop. So that's what we're dealing with here. All right, the Doppler effect. I'm going to switch to a video now, which means I'm going to flip the switches. However, the video will be sent in the email, so this concludes the recording of this video.